Oh, you're welcome back. All right, so the topic before us is ordinary differential equation. Okay, so we're going to start by defining the term differential equation. Okay, now it's differential equation simply. Okay, it's made up of two words, differential and an equation. And of course, you know very well that the word differential also imply derivative. Okay, which I believe that you must have actually you have studied derivative, then you now have equation, right? Of course, I believe also you know what an equation is. So combining the two words together, okay, so we can define another differential equation as an equation that actually contains derivative. So it is an equation, okay, but the component of the equation, one uh, vital component of the equation is the derivative it contains, okay, like what you see here. Okay, so now I can actually um, extend the definition to to go this way. Ordinary differential equation also it can be abbreviated as ODE. Okay, is an equation. It's an equation that contains okay that contain one or more. Okay, it can be one or more derivative derivative of an unknown function. Okay, so we simply means that it's an equation, but what makes the equation unique is that it must have a derivative. So like the example I give here, the y s plus 9s is equal to 0. This is an equation, right, which contains the derivative. Now it is the derivative of an unknown function. So the unknown in a differential equation is a function. Okay, the same way you have the unknown, okay, in a linear equation is just a variable. Okay, but this time around, the unknown in the differential equation is a function. So if you are being asked to solve differential equation, you are also being asked to find the unknown function of the differential equation. So when you solve this differential equation, you end up having y, okay, being equal to a function of x. So that is what you end up having when you are being asked to solve this differential equation. Okay, so I hope that introduction is well understood. All right. Okay, please pardon me. Okay. So let's proceed. Okay, let's proceed. Now, okay, so we're going to be looking at the different types. Okay, we're going to look at the order of ODE. So, but permit me to use the abbreviation ODE, order of ODE. Okay, now the order of ODE actually can actually be found by getting to identify the highest, okay, the highest order of derivative, the highest order of the derivative in that function. In the equation. So the highest order of the derivative of in the equation actually shows the order of ODE. Okay, now let's look at them one after the other. Okay, now for first order ODE, that simply means that the highest order of the derivative in the function, okay, is the first order. For example, dy dx plus y exponent x equal to 0. This is first order ODE, okay, because the derivative is just first order derivative, all right? Then we can also have second order ODE, okay? Second order. All right. Now for second order ODE, the derivative, okay, the highest derivative, okay, the highest order of the derivative of that ODE is the second order. Okay, you will also have the lower order of derivative in the equation, for example. So something of this nature, 2x d square y all over dx squared, okay, then plus y dy dx, then plus exponent x y equal to 0. So once you see such, okay, descending order of the derivative starting from the second order, now this actually shows that this derivative here is the second order ODE. So I hope that is well understood. Okay. Okay, so now what we are going to do, okay, so we are going to start with the solution of ODE. Now, how do you actually solve ODE? Solution of ODE. Now, as I already told you, anytime you are being asked to solve ODE, all right, you are invariably asked to find your known function. Now, when an ODE can actually be expressed implicitly, uh, explicit, okay, explicit, okay, or you put it this way, an explicit ODE is an ODE that you can, the variable, separable variable. So that simply means that such ODE, you can actually separate the derivative from the derivative, okay, the derivative or the change, the derivative, the change of each function, okay, from each other. Let me give you a typical example. Now, when ODE is of this form, dy dx being equal to function of x and y, dy dx, okay, separated from the actual function of x and y, such ODE is said to be separable or it is explicit, okay. It is explicit. The derivative separated from this function. All right. Now, please take note of this. Derivative can also be written as y prime. Okay. I believe you know this already. So you can also write this as y prime. Y prime function of x comma y. Let me give you a typical example. Okay. Um, Typical example. Okay, let's look at y prime being equal to 2y exponent x. So this is separable ODE. Okay, explicit. But and the solution to this is much easier. Okay, you can just solve this ODE by separating variables, which we are going to start. So we are going to start with the explicit ODE. But when the ODE, all right, and the functions of x and y are implicitly connected, or it cannot be separated, so you can say it as that is implicit. Okay, or not separable. So in such a case, higher technique of solution is actually needed. So when you do this of this form, function of x comma y prime, okay, the derivative and the function of x and y, all right, are the function of x and y and derivative are inseparable, right? So such a OD is actually implicit. Now, so to solve this, okay, the technique we're going to employ a more a complex technique depending on the nature of the ODE to solve it. So we are actually going to start with this one, okay, with the separable ODE. So now I'm going to solve the few example, then we'll continue. Okay, so let's look at okay, so typical example is what I gave here. So I can solve this one right here. Y prime is equal to 2y exponent of x. All right. So of course we can actually write this the y prime, okay, in terms of the y dx is equal to 2y. So now we can separate the variable. What do I mean by separating variable? You separate uh, the y and of course the function of y at one side of the equation, right? Then the function of s with the s at the other side of the equation. All right, so now to do that, the very first thing I'm going to do is to cross multiply, okay? So that I will not have a fraction. Let me cross multiply. By cross multiplying, I'm going to have the y multiplied by y will give me the y. Then I have 2y exponent of x. Okay, so I can now separate the variables. So 2y exponent of x, please pardon me the x. So what am I going to do now? I'll take 2y to the other side of the equation. Okay, so I'm going to have the y, okay, divided by 2y. All right, and it's equal to Okay, exponent of x dx. So now, how do we now solve this equation? Having separated the variable, okay? To solve the equation, we integrate both sides. Integrate both sides. All right, so we'll find the integral value of dy, and of course, you have to write this 2 as a constant behind the integration. So it is still the same technique to solve this integration. It's still the same technique of solving integration, the same properties of integration. That's what you apply here. Okay. Okay, here we go. So now, okay, so let's go. So I'm gonna integrate both sides. The integral value of, so 1 all over 2, I take it behind the integration sign. So here I'm going to have 1 all over y dy, then the integral value of exponent of x dx. Okay, so this is going to be 1 all over 2. If you integrate 1 all over y, okay, the reciprocal of y, I believe you know that that's going to give you ln x. Okay, and if you integrate exponent of x, you have exponent of x. All right, now it is only one side. Okay, we only have just one constant after integrating. We will not have two constants. Okay, please take note of that. So we'll rearrange the equation. Please pardon me. The integral value of 1 over y is ln y, not ln x. Please pardon me. Okay, so we only have one constant. Okay, so just have one constant. So invariably now I can cross multiply and I have ln y equal to exponent of x plus c. Okay, multiply by 2. All right. So for me to get y now, I can find the exponent of both sides of the equation. All right. I can take the exponent of both sides of the equation. I can do exponent ln y. That will equal to exponent of 2 exponent x. Okay. Then plus 2c. All right. So in this case now, I needed to eliminate the ln. Okay, that's why I take the exponent of both sides. So exponent cancel ln. So I'm left with exponent of 2 exponent x. All right. Then plus c. So I can do something to this. Applying the law of indices. Okay, you know that applying the law of indices, this is also equivalent to exponent 2 exponent x. All right, then times exponent c. Exponent 2c, please. 2c, pardon me. Exponent 2c. Okay, so you know that this is law of indices. If you use law of indices to work on this, okay, they are the same. All right, so the reason I want to do that is that the whole of this is a constant. It doesn't have any variable. Okay, so I can just call it any constant. I can just use k to represent that constant, because at the end of the this um okay, I can use k to represent this constant. Okay, so my final answer now will not be k exponent 2 exponent x. Okay, so I hope that is well understood. I'll still look at more examples. So now this, anytime you solve ODE, you end up having, okay, uh, you end up having a constant, which of course the value of the constant, they don't know what it is, okay? So that will lead us to two type of solutions. There are two types of solution, okay? And I will discuss those two type of solution, and the type of solution that will enable you to actually get the constant of the solution, all right? So, but before then, we are going to look at more equations. We are going to solve more equations, and we will do that in the next video, all right? So see you in the next video. Thank you very much.